Here are some more predict the product questions. The substrate in this case is a secondary substrate, and we have a what we would call a strong base, strong nucleophile, and so we would expect probably E2. So let's look back at our chart. This chart is from your textbook, and I think at first glance, well, let's figure out where we are right now. We have a strong base, strong nucleophile, and we have secondary. So we're going to look for major elimination product, minor substitution product. As far as being able to understand this chart and use it on questions like this, either on a quiz or exam, at first glance it looks very complicated, but I would propose that it is not actually that complicated. So here's my thoughts about this chart. The nucleophile only section is straight out of chapter 7. So as long as you could handle the questions at the end of chapter 7, primary goes SN2, tertiary goes SN1, secondary you got to kind of decide based on probably the solvent. That's the first part of the chart. So you've got the top quarter beat. The second part of the chart, the base only section, DBU and DBN are kind of new bases here, and if you understand it, they're just large non-nucleophilic bases. They act as good bases. Same with T-butoxide, which we've seen already. And then hydride, which we see occasionally, but we don't often use it as a base. So there's really only a couple of choices for base only. And if we do decide it's base only, well, there's only one outcome regardless of the substrate type. So that's pretty easy to understand. If we have a base that can't be a nucleophile, we're going to get an E2 reaction. So the top quarter is from chapter 7. The second quarter is a few types of reagents that we can remember pretty easily, and all lead to E2 reactions. When we get to the strong nucleophile, strong base section, that gets a little more dicey, but really, again, unless it's primary, where the substitution is major because primary has less sterics, secondary, tertiary lead to E2 just like they did with base only. So if we have basically methoxide is a good example here, ethoxide, and really any sort of alkyl oxide. We're not going to get much more complicated than propyl oxide here, or OH minus. Those are all good nucleophiles and good bases, and if we have a secondary or tertiary substrate, the major product's E2. Otherwise, sterics play a role, and we get a substitution with our primary substrate. So that's maybe a little more complicated, but still it's reasonably straightforward. The sterics here play the role of deciding what's going to happen. And lastly, if we have some alcohol or water, and that's really the only combination. So oftentimes here our substrates are ethanol, methanol, or water. That's a weak nucleophile, weak base. And you'll see that primary and secondary substrates are really not practical to react in this manner. So we're not going to ask you to predict the outcome of primary and secondary. There may be a case where we give you this reagent and we give you the product. Let's say we imply that it's SN2 by our product. We might ask you for the mechanism, but I wouldn't ask you to predict whether which reaction is going to take place if we have a primary or secondary. However, tertiary is where we can sort of make the distinction, and if you remember from the text, heat can be used to influence E1 reactions. Excuse me. And so if we have a weak base with heat and a tertiary substrate, we might expect E1 as our outcome. No heat, probably going to be an SN1 type of reaction, but it'll be kind of slower. And if we can do it using SN2 type chemistry or E2 type chemistry, we'll probably choose that route anyways because it's a bit easier. And of course, we don't form the cation intermediate as we would form in SN1 or E1. And that cation intermediate can often lead to lots of issues. And that's pretty much why secondary substrates are really not any good to react with weak nucleophiles and weak bases, because you can basically just get any sort of reaction to occur. There's really no control. So this chart is, I think, a lot simpler than we see at first glance. There's chapter 7, the top part of the chart. There's only a few reagents that are base only, and they all lead to the same outcome, so that quarter is pretty easy to understand. Strong nucleophile, strong base typically gets you E2 unless you have a primary substrate. And then with weak nucleophile, weak base, we're not going to ask you to predict these products here. We might ask you for a mechanism, but we'll give you the product in that case. Whereas with a tertiary, that might be the hardest sort of category in this case, the weak nucleophile, weak base with a tertiary substrate. If we add heat in our reaction, we will probably assume that the E1 is the major product. If there's no heat, you can predict that the SN1 product is the major product. So let's go back to our discussion here. We have secondary, strong base, strong nucleophile, and if you remember from the chart, E2 is favored, and maybe a little bit of SN2. So let's go ahead and draw that. We need to figure out the location of the beta hydrogens when we're dealing with an E2 reaction. So that's really why we want to know that it's E2, so that we can look for beta hydrogens and decide how they're going to react. So I think I need to draw a Newman projection here, because if I remove HA, there's only one option for hydrogen on this carbon. And so that tells us we're going to get stereo-specific results from removing HA. And now how do we predict that? We need to draw a Newman projection. So let's go ahead and do that. I think we are in the eclipsed form right now, so this might get a little dicey for a minute. There's the BR, here is HB, it's eclipsing HA, and then here is, no, I'm sorry, that's not HB, that's just a methyl. So here is the methyl coming off of that, and here is some hydrogen we're not going to label because it is not a beta hydrogen. So I need to rotate this so that HA is directly opposite the bromine. So I'm going to rotate the front carbon, and I end up with this. And I'm going to try to move this stuff here. We'll fix that later. So I rotated the front carbon, and that means I have isopropyl, and I have the methyl, and then the bromine is straight up in the back. The methyl is still there, and the unlabeled hydrogen is right there. And so now I'm ready to undergo my E2 elimination. And of course this is sort of the pathway, and we would get methyl and isopropyl on one side of our alkene, and then we would get unlabeled hydrogen and methyl on the other side. And we just need to make sure we put them in the right spot. So I have a methyl, and if I were to draw in, here's the unlabeled hydrogen, he's supposed to be opposite the methyl, and then the isopropyl should have the other methyl. And so in this case, I get, let's see, higher priority. This is the Z version. We're not going to get any E, only isomer formed. And so that's minus HA. And of course, we can also have minus HB, but it's a lot easier to do that because on a methyl, there's no stereoselectivity, nor is there any stereospecificity. It's simply create the alkene. And so if we have a mechanism that goes like this, there's only one possible alkene that we can get here. And it's going to look like this. So here's the unlabeled hydrogen. Here's HA that wasn't affected. And so this would be a minor product because it is the Hofmann. It is the less substituted alkene. And it's also possible to get a minor product from the SN2 reaction. So let's draw that quickly. We want to invert here. All we have to do is change any wedges to dashes or vice versa. So I'm going to do that. And I've changed my bromine into a methoxy group. This would also be a minor product. And we can label that SN2 if we want to. And so these are the E2 products. They're going to be major products. So there's probably more of this than there is of the substitution product, but we'll label them both minor. We're not going to get into exactly how much of each there are. So let's look at this reaction now. I'm going to move it up a little bit, and then I need to fix this line here. So this reaction is tertiary, and we would label this certainly strong base, or we might even say base only. Either of those is fine. And if you refer back to the chart, as I said before, with base only, there's only one option. Here's base only. All of them lead to E2, so let's draw an E2 reaction. And of course, with the large bulky base, we're going to favor loss of the more accessible hydrogens. And so if we draw that, this is minus HA. That would be the major product because we have a large bulky base. It favors the Hofmann elimination. And this is, of course, E2. And then we could lose HB right here. And there's no stereochemistry associated with this alkene because I have two methyl groups on this carbon. So there's no way to establish a priority here. They're both the same. So it's not E, it's not Z, it's just an alkene. And of course, this is the minor product. And that is the Zaitsev. And it's minor because the base has harder time accessing HB than it does HA. And that's because we have this large, bulky base. If we used a small base, let's say methoxide, we would expect the outcome to be reversed. The Hofmann would be the minor product, and the more thermodynamically stable Zaitsev product would be the major product. And that's because the smaller base has an easier time accessing the interior hydrogens.